Okay, so in this problem, we've got a signpost fixed at the ground. I've got wind basically pushing on with the pressure of 7 pounds per square foot, perpendicular is shown, so against that sign. And I want to find those internal loadings at point B on that post as shown. So I'll start by drawing a free body diagram of, I guess I should say, since I'm trying to find the internal loads, I want to cut it at B, draw above there. I don't need to find the reactions here because I've got all the loadings on the top piece. So what I'll do is I'll go ahead and just draw the top part of this problem and solve directly for those internal loads at B. Now this is in 3 dimensions, so it works a little different. Okay, so we start with the sign like so, and essentially I've got a force pushing on it, which is essentially the pressure of 7 times the area, which is 3 times 5. Okay, so that's pushing on there. Notice that's good. The post is a little bit off center. I'll draw quite a bit off center just to be exaggerating, right? So it's going to cause some twisting as well as some pushing on this guy. Now at B, we've got forces. We've got the normal force that we're used to. I'm going to draw everything just in the positive directions. I'm much bigger fan of figuring out looking at the picture, figuring out the direction than a traditional sign convention. So at this point, I'm just going to draw a force in the positive z direction. That's my normal force. I haven't drawn in compression. Typically, we draw it a positive to be in tension. But again, if you look at the picture, you can figure out what direction these things are in. Okay, I've got a shear force in both the x and the y direction. Okay, so I'm going to call that bx and by. Okay, and again, I'm just going to draw those in the positive directions based on the the coordinates, right? Now I've also got moments on this. Now I've got bending moments. Now this bending moments, I'm going to have one about the y direction. So I'll call that m b y. I also am going to have one about the x direction. M b x. And then I'm going to have a twisting one that goes around the z axis. And again, I'm just going to draw these all in the positive direction. MBZ. It's not the best M, but you get the idea. Okay? So basically, with 2 directions, I just have shear, normal, and bending moment. Here I have the normal, 2 bending moments, 2 shears, and then I have a twisting that we call torque, and we'll talk about that in a later chapter. Okay? But I need to find the internal loads of all of those in this sort of a problem. Okay? Now, this is we're basically going to ignore the weight of things on here. Okay, so we're just going to worry about what's going on with the wind. We'll assume the wind is much larger than the weight of any of this. Okay, so that's it. That's my free body diagram. Okay, so now that we've got that, we just start applying our static equilibrium equation. So I'm going to sum the forces in the x direction, which is going to be that negative 105, and then the positive bx, right? That shear force in the x direction, minus 105 equals 0. That means that the shear force in the x direction is in the positive x direction and equals 105 pounds. Okay, now the easy ones, summing the forces in the y direction, I don't have any other applied load, so that's going to say that by equals 0, and it's also going to say that bz equals 0, again, because we're neglecting weight. If there was a weight, then there would be some compression that was going on due to that gravity, but we're going to ignore it here. So that's bz equals 0. We're going to assume it's negligible compared to what's going on with that wind force there. Okay? Now we have to do the moment equations, and when I do moments in 3 dimensions, I just do them in 3 dimensions, then split them out. And we'll talk about what each component equals as after we split them out. So I always sum my moments about where I cut. So I'll do that. I've got 3 bending moments that I have to worry about. I've got mbxi plus mbyj plus mbzk. All right? Then I have the moment due to the um, the the wind that is pushing on the sign, please, on the sign of 105 pounds. Okay, and that's going to create several different moments about B. Okay, so basically I'm going to go R cross B to figure this out. So my R, I move basically in the Y direction, and this is going to be pushing at the center of that sign, which is actually a half a foot off, right? Because that would be at 2.5. My pole's at 2, so I actually move negative 0.5 in the J. So negative 0.5 in the J. Okay? And then I move up to the center of that, up 6 feet to the bottom of the sign, and then another 1.5 to the center of that sign. So that's going to be plus 7.5 in the K direction. Okay? And then I'm going to cross that with that force, which is in the negative X direction. So it's going to be crossed with negative 105I. So again, it's just R cross F from B up to the center of that sign times that force in the negative X direction. Okay, so doing the cross product on that, I get negative 52.5 K and negative 787.5 in the J. Again, that's from the J cross I and the K cross I. So about the K axis, that's actually the twisting. So that's the 0.5 over twisting that around that post. The 787 is from that 7.5 feet times the 105. So that's like it trying to bend it over about the negative Y axis. Okay, so now I can go ahead and separate these out, and I can say, okay, in the X direction I have mbx, and that's it. That's the only thing in the X direction, so that equals 0. So there is no bending moment about the X-axis. Now, had this had a weight that we would have concerned with, we would have had a small moment about the X-axis, but again, we're assuming it to be negligible, so we just ignored it. In the Z, or in the Y direction, I have, again, mby minus 787.5, and that equals 0. So from that, I find that mby is 787.5, and my units on this are going to be foot-pounds. Okay, so again, that is the bending moment about the y-axis. Again, this thing trying to kind of be pushed over by the wind. In the z direction, I have mbz minus 52.5 equals 0. That tells me that mbz then equals 52.5 foot-pounds. And this is basically the torque that's being created, and that would be like the twisting about the pole that's created at B. Okay, so again, just like in 2 dimensions, cut it where you want to find what the internal loads are, and then apply your equilibrium equations. The difference is now you've got 2 shears, 2 bending moments, you've got a torque and a normal force, okay? And for what we have here, we have a shear force in the x direction of 105. I have a bending moment about the y-axis of 787. And then we've got a torque or a twist about the z-axis of 52.5.